Hi, I'm going to present our work on pre-computation of, global illumination for real-time rendering of static scenes. So the goal of our method is to achieve, to perform pre-computation so that we can perform interactive walkthroughs. So here I'm showing our method running on two different scenes. Interactive walkthroughs are useful because they can be used for architectural visualization or cultural heritage exploration. They can also be used for generating a lot of training data that is required for modern data-hungry models such as diffusion. So I'll first talk about what the problem is. So to render an image, we usually need to solve the light transport equation. And what the light transport equation does is it takes at every shading point, it takes the incoming radiance, it modulates it with the BRDF, which is the appearance, and it gives you the outgoing radiance. Usually you do not have a closed form solution for this, so you need to perform numerical simulation, such as Monte Carlo path tracing. At real-time frame rates, you can't perform a lot of samples, and that gives you a lot of noise, which basically is hard for denoisers to deal with. Recently, with the advent of spatio-temporal reuse methods such as Reester, this has become better. So what these methods do is they reuse data from previous frames to reduce the variance. However, there can still be some scenes where the light paths are too difficult for these to deal with. Traditionally, what has been used is something like probes, where you place probes uniformly in the scene, and then you basically pre-compute the radiance information in these, and at runtime you interpolate them. The issue with these is that these are usually non-adaptive, and they have a lot of pre-computation required. Recently, with the advent of neural networks, neural methods have been applied for the same. So they usually work by putting in the G buffers as the input, and like it's trained per scene. These still have quite a lot of pre-computation time, and they are not real time to render. An explicit representation was also proposed, which also has high pre-computation time, and it's not real time to render and has some artifacts. So basically, we wanted to try and solve all of these issues. So what we do is we propose an hybrid approach where we try to pre-compute and store most of the complex light paths. And wherever we know that our pre-computation is going to fail, we do a small lightweight path tracing. So specifically, we contribute an explicit representation, which is lightweight and which allows for real-time rendering. We then we propose an optimization-based pre-computation strategy, which is efficient and tries to reduce the amount of pre-computation required. And finally, we propose an efficient renderer, which supports rendering complex light paths. Now I'll talk a bit about our representation. So going back to the light transport equation, we need to decide what we want to pre-compute and cache. So since we already have the geometry and the BSDF from the scene description, we have two options. We can either cache the outgoing radiance or the incoming radiance. We decide to cache the incoming radiance. Why would we want to cache the incoming radiance? Turns out it is an easier signal to pre-compute and cache because it doesn't depend upon the material properties and the geometry. So it's much more smoother and it's easier to store. So what we do is we try to store the incoming radiance using a spatial-angular Gaussian mixture model. So our primitives are basically a product of 3D Gaussian, represented by the ellipsoids over here, and an anisotropic spherical Gaussian, which models the angular variation, represented by the lobe over there. And these parameters are optimized using stochastic gradient descent. With this naive formulation, though there is a problem. So in this scene, we see that the the primitive is trying to model the plane above. So if we evaluate the primitive at the center, it's fine, it's pointing correctly. But if you, let's say, evaluate it at another point, the lobe is no longer pointing to the plane. So we need to fix this. So what we want is basically, depending upon where you evaluate the primitive, you want to change the orientation of the lobe. And we do this by optimizing a transform per primitive, which takes the position at which you're evaluating the lobe and then converts it into the orientation of the ASG. So this is our modified spatial-angular Gaussian mixture model. And since we are storing the incoming gradients, we need to perform a final integration step because we need the outgoing gradients at the end to render. And here we make use of the nice properties that ASGs have. So if you represent the BSDF as a Gaussian mixture model made of isotopic spherical Gaussians, you can use the closed form solution for the integral, and basically the light transport equation converts into a double summation. And usually for most BSDF, it's you only need a single lobe, so it's usually a single summation. So now I'll talk about our optimization strategy. So we optimize in world space on 3D points which are sampled on the surfaces of the scene. We compute the outgoing gradients at each of these points using Monte Carlo path tracing. And since the outgoing gradients is in HDR, you need to apply a log loss on these. So if we are storing incoming gradients, why are we optimizing on outgoing gradients? There are two main reasons. The first is that at the end, the thing that we are going to render is the outgoing gradients. So we want to reduce that, we want to optimize for that. And also, we need to also consider the fact that a BSDF acts as a low-pass filter. So as you can see on the right over here, we see the outgoing gradients for surfaces with different roughnesses, and for higher roughnesses, you basically need much less detail, and you want to adapt for this. So if we optimize on the outgoing gradients, our representation automatically take care of this. It doesn't need to represent very high frequency stuff. So here I'm showing the learned representation after an optimization. So on the diffuse wall, you only need to learn the average incoming gradients as seen on the right. Whereas on glossy surfaces, you need to learn the representation learns it in a bit more detail. We also propose an initialization strategy which tries to initialize primitives in the regions where they are required the most. So what we want is we want to place primitives at shadow boundaries, and we observe that most of the shadow boundaries happen because of direct lighting. So what we do is we compute the direct lighting at each point. We compute a spatial gradient that gives us like the regions where we want to place more primitives. We also want to place more primitives in the regions of high curvature. So for this, we compute the harmonic distance, which is kind of like ambient occlusion. And we basically sum this up together to give us a PDF on which we can sample our Gaussian primitives. So here I'm showing our initialization results. We can see that we have more primitives near the shadow boundaries and in the regions where there is change of curvature. Here is an ablation. If you see on the metal wall behind, if you start uniformly, you do not have the shadows, but with our initialization, we have the shadows which are better reconstructed. We also need to do some densification and pruning because the things that I described, the initialization strategy, it can fail sometimes. So we want to be able to add and remove primitives as we go. For this, we make use of the frequency estimate of our representation. So we noticed that Gaussians have this notion of frequency, where smaller Gaussians have higher frequencies than bigger Gaussians. So basically, we want to place new Gaussians in the regions where we have high frequencies. So we want to kind of take this into account. So to do this, what we do is we compute for each primitive, we compute its spatial frequency and its angular frequency. We also compute its error contribution, which is basically for each of the point it covers, how much is the error. And we use this to build a probability, and we sample this probability to add new Gaussians. And for the pruning, we want to remove primitives from overrepresented regions. So to do this, we add an regularizer, which tries to make the Gaussian smaller. And then we have like a simple threshold-based pruning strategy, where if a Gaussian is not covering enough points, you just remove it. And here is a video which shows the distribution of Gaussians as we go. And as you can see at the end, we have less number of Gaussians on the walls, where it's smooth, and more number of Gaussians in the shadow regions. An ablation for this, if you see the reflection of the oven, without densification, the reflection isn't captured. However, with the densification, the reflection is captured. And on the wall, you have some overrepresented regions which are removed by the pruning strategy. Finally, we want to also reduce the number of points that we use for optimization, because computing these ground truth points is expensive. So we reuse the idea of frequency estimates to only place points where they are needed the most. So here I'm showing for each point the highest frequency Gaussian that it is covered by, and basically we want to place more points in the white regions and less in the dark regions. So what we do is we start with an uniform sampling, and then we keep on as the GMM progresses. It better approximates the radiance field, and we can make use of this to add new points in the regions where it's needed the most. So here I'm showing the density of ground truth points as the optimization occurs, and we can see that most of the points are added in the shadow regions. And here we have an ablation. So the pre-computation time with this reduces by almost 50%, and also some highlights such as on the table are recovered, because the adaptive sampling can better focus on the regions where it's needed. And finally, I'll talk a bit about the rendering. So to efficiently render this, for each point, we need to find out the primitives that it affects. So to do this, we basically build a BVH on the Gaussians, and then we traverse down the BVH to find out all of the relevant primitives which enclose the point. And the good thing about this is that you can do this with hardware RT cores, and it makes it really efficient. Concretely, to render, we start with the first bounce. We shoot a first ray from the camera. We query the BSDF. If the BSDF is quite broad, you just find out all of the nearby Gaussians, and then you perform the integration using the closed form solution. For narrow BSDFs, our representation is not sufficient, like something like a mirror or very, very smooth surfaces. In that case, we sample the BSDF lobe and then evaluate the GMM at the second bounce. And then for this, we need to use an denoiser to get rid of the residual noise. So here we have an ablation on that. So as you can see, the reflection of the mirror and the reflection of the kettle are better reconstructed with the second bounce. And with that, I will go to the results. So we compare against both pre-computation-based methods and real-time path tracing methods. And here we see that we have extremely low pre-computation time compared to the others, and we have better quality than them. And finally, I will show some interactive walkthroughs. So for this scene, the pre-computation time was about 4 minutes, and it's an artist-authored scene. I'll skip this, but the video for this is available on the website. And we also, I will also show you some comparisons with other methods. So this is with a path reuse method. So as we can see on the highlights of the table, the path reuse method, restart-fg, kind of struggles with the highlights, versus since we do the pre-computation, we don't have to worry about it. So as on the reflections of the chimney. This is with dynamic neural radiosity, which is a neural network method, and you can see the reflection of the chair is not well reconstructed, and the glossy effects on the chair are not that well reconstructed by the neural method. And finally, this is with neural incoming radiance caching, which has quite a high amount of bias in the back wall. And yeah, so our method is not without limitations. So since we perform a second bounce on very smooth surfaces, and we need to use a denoiser, there is some amount of temporal lag that is induced. And also we kind of struggle with reconstructing very small shadows. This is because the pruning strategy is dependent upon the number of points that a primitive covers. And if the shadow region is very small, it doesn't have enough primitives, enough ground truth points, and hence the primitive always gets pruned out. With that, I thank you for your attention, and there's a project page if you want to see more about it. Yeah, thanks.
Thank you for the talk. You mentioned that when the lobe is very small, you continue and you won't use denoiser. So do you have like a local metric contribution to that to automatically pick if you need a denoiser or not?
Whether we want to do a second bounce or not?
Yes, we automatically detect if you need to go to second mode.
So yes, we have we reuse a metric that NIRC proposed. It's called the balanced termination heuristic, which basically compares how glossy it is compared to a diffuse lobe, and we probabilistically sample this weight, and then we decide to shoot array based upon that.
Okay, thanks.
Hey, I was wondering about this parallax compensation transform that you're learning. How exactly does that work? Can you sketch that?
Yeah, so it's basically just a 4x3 matrix and a 4 bias vector. So it's a very tiny MLP if you think about it. So the 4x3, you take the position that you're querying the primitive at in the local coordinates, you multiply by the 4x3 matrix and add the bias vector. And then you get a quaternion as output, which you normalize, and that represents the orientation of the lobe. Yeah.
Sounds simple enough, thanks.
Yeah.
All right, let's thank Ishaan one more time.
Thanks.